Greetings physicists, and welcome to your chapter 32 lecture video on the structure of the atom. Now by this point in the semester everyone probably already knows what atoms are made out of. Protons, neutrons, and electrons, and those of course are made up of quarks and so on. But how do we discover these particles, and how do we know what the structure of the atom actually looks like? Those are important questions, right? So we're going to start off today with the famous Rutherford's gold foil experiment. And I had planned on doing a simulation for you, but unfortunately that's quite impossible. And so instead what I'm going to do is I'm going to draw you a diagram. Also, if you look in the description or on the chapter 32 lecture page, if you look there, there's also a link to a YouTube video that has an animation showing exactly what I'm about to show you now. So, once upon a time, a guy named Rutherford took an alpha particle generator, or an alpha particle emitter, right? Just like a box that, whenever it decays, it emits an alpha particle. Everybody remember what that is? That is the nucleus of a helium atom. It has 2 protons and 2 neutrons. That is an alpha particle, is what we usually call it. Now sometimes when things undergo radioactive decay, as we're going to see very shortly in upcoming chapters, sometimes something will decay into a lighter element and spit out one of these alpha particles. We call that an alpha particle emitter. And so they took some radioactive sample of this alpha emitting stuff and they put it in a box so that there was a tiny little hole, and the alpha particles could only get out through this hole, and they would all basically kind of be going in the same direction. And out here they placed a little piece of gold foil. Actually, let me try and center this a little better so you can get a better idea. I'm sorry, I'm a terrible artist. In any case, let's say the alpha particles are shot out this way, and there's a little piece of gold foil here. Now, they put around it this film. It was made out of zinc sulfide, and when any of these alpha particles hit it, it would expose and sort of make a mark at this point, wherever the alpha particles struck. And what they saw when they sent this alpha beam at this gold foil is most of them went straight through and hit locations here on the back. Some were deflected a little bit, some were deflected a lot, and some were deflected almost 180 degrees. Now, the shape of something that's going to be able to deflect something 180 degrees, but also be able to deflect something kind of a lot and kind of a little, has to be basically circular or spherical in this case, right? We're talking about a 3-dimensional kind of distribution. And so from that, Rutherford was able to infer that the particles, whatever this gold is made out of, has to have a really dense circular, or spherical part in the center so that these alpha particles could rebound off it in these geometries. Nowadays, we call this the nucleus, right? That's where all the heavy particles, the protons and neutrons, live in an atom. And so that's good for us understanding that there's a nucleus. But electrons, the other major part of an atom, don't live in the nucleus, do they? So how did we find them? Well, that really started with this thing that we call a cathode ray tube. And the classic example of that, of course, is those fluorescent tubes that they have like in the classroom. So you have basically a metal plate here, you have a tube, and you have a metal plate here. One of these is charged negative, one of these is charged positive. The negatively charged side is called the cathode, and the positively charged part is called the anode. Now, we both know that the actual charges that are free to move are these negative ones, the electrons. And they're going to be attracted to the positive charge over here, the net positive, and so they'll stream across sort of in rays, hence cathode ray tube. This is like what the old TVs were made out of and so on. But in any case, when these electrons would be excited to move from one end of the cathode ray tube to the other, they would stimulate whatever phosphorescent was on the inside of the glass, in the case of the fluorescent light bulb, and that would cause, the fluorescence, right, and the brightness. But that's not how we found electrons. What we did when we found electrons, or what J.J. Thomson did, right, was he took the anode and cut a tiny little hole in it, right? So we put the anode sort of more towards the center, and when a bunch of these electrons would get attracted, some of them would go right through the middle, through the hole in the center. And so that's how we were able to figure out that there was a negatively charged particle, when you set up your detector over here or whatever, that it was a negatively charged particle, this thing that we call the electron, that was moving through these cathode ray tubes. Now, J.J. Thomson was a very clever human being, and he also figured out that if you put a magnet here, right, you could deflect the ray. Everybody remembers that electric fields or charges can affect magnetic fields and vice versa, right? Well, it just so turns out there's this thing called the Lorentz force law, The force on a charged particle is equal to the magnitude of the charge times the velocity of the particle, taking the cross product with the magnetic field. Now this is a funny geometry. This x does not mean times. It's this funny thing called a cross product where you have to use the right hand rule. Suffice to say, if you got a magnetic field going this way and a charged particle going this way, they have to be perpendicular to each other. So let's say this made a magnetic field down. QV cross B means that it would actually deflect into the board, but you don't have to know that, okay? You just have to know that if a charged particle enters a magnetic field, it will feel a force. We talked about this before, if you recall. In any case, he called, J.J. Thomson that is, called the charged particle the electron. Well, we didn't know the mass of the electron until Robert Millikan performed another famous experiment where he essentially had two plates, and I talked about this one before also. Using an electric field, he made droplets levitate in between two charged plates. And from that he was able to figure out the mass to charge ratio by deflecting the path of the electron cathode rays and then the mass themselves by comparing it to gravity, right? Making these tiny little atomized droplets of oil, with which he figured he could count the individual electrons, right, by their orbitals. That led him to find the mass of the electron, like we mentioned last week, and that earned him the Nobel Prize in Physics in the year 1923. Go Robert Millikan. In any case, that brings us to the Bohr model of the atom. Now, we already know that different atoms, different elements, if you will, have different emission spectra because their energy levels are quantized, and one of the electrons gets excited and de-excites, it'll emit a photon corresponding to the energy difference. The reason that these energy levels is quantized goes back to this funny thing that we call the de Broglie wavelength, because matter can only exist in stable states. So if we want to use the standing wave generator as an analogy, right, we can see that matter can only exist in certain quantized states. So let's say you've got this wave pattern, right? You've got two full wavelengths in whatever distance you have here, right? So let's say that this is your orbital. You start here, above, below, right? So this is actually stable, but you can't have, say, 1, 2, 3, right? Because that would bring you, I'd really like to draw this in another color just to show that this is wrong. So let's say you go above, below, above, and then if you try to go back to below and then below again, the directions of these contradict each other, right? This is supposed to look more like this, I apologize. Above, below, above. This should come all the way around like this. In any case, you see that this one is pointing downward towards the nucleus. This one is pointing upward towards the outside, right, away from the nucleus or towards the electron orbitals. And what that means is if this was going to be the electron's actual path, right, its energy level, then it would have to suffer a spontaneous reversal of momentum. And particles just can't do that. If you want to change something's momentum, you have to impart a force on it over time. Remember, we call that an impulse, right? Things don't just spontaneously reverse their momentum, and so this is not a stable state. It's only where these actually can constructively interfere with themselves, right, where they make a stable wave pattern, that these particles can exist in these electron orbitals. So there are no quarter or third wavelengths or halves, right? This is 1.5 wavelengths, etc. They do not exist. It's only full integer number of wavelengths. Physicists, have written the probability distribution as a mathematical function, describing the location of the electron in a stable state, called the wave equation, named for Erwin Schrödinger. And if you remember, the man who we attribute Schrödinger's cat to. Okay, that's about it for chapter 32. Please take your quiz for understanding. As always, if you have any questions, please contact me, and I'll see you for chapter 33.